All right, let's talk about cryptographic solutions, or otherwise known as cryptography. And this is how we are going to secure data through encryption, authentication, integrity checks. And cryptography itself is really just trying to get data into an unreadable format just in case an unauthorized user receives it, and they won't be able to reverse engineer that data into the actual data. This is just for us to ensure that authorized users are the only ones that are able to see said data. And there's also some integrity aspects to encryption, like hashing and using digital signatures to verify that data itself was not modified during transmission or storage or even in processing. So let's get to it. So, what is cryptography? Well, it's the ability to transform data into unreadable format, encryption, to provide its confidentiality and prevent authorized access. There are different areas in encryption that we're going to talk about cryptography solutions that we're going to talk about. One of the areas is going to be encryption, which is all about converting data into ciphertext that can only be read by someone with the correct deciphered key. So we're talking about decryption and encryption here, and if they can decrypt the text by using the proper decryption key, this is how they can get back to readable text. We're going to talk a little bit about digital signatures, which is verifying the authenticity or the integrity of messages or files, and making sure that they really did come from a trusted source and they have not been tampered with. Talk a little bit about hashing, which helps us create a unique fingerprint and to make sure that the data again remains unchanged, and it's very commonly used to ensure integrity of a file. And then lastly, we're going to talk about PKI, which is public key infrastructures. So how do we manage all these keys and certificates and use them for communications and authentication? So the first concept that I like to reach out to is going to be symmetric versus asymmetric. Symmetric cryptography, also known as secret key cryptography, uses a single key to encrypt and decrypt a message. This means we'll use the same key between the sender and the recipient. Symmetric encryption is fast, efficient, and suitable for using it for encrypting large amounts of data, but does have its downfalls. An asymmetric key, on the other hand, or asymmetric cryptography, also known as public key cryptography, uses a pair of keys. It has a public key for encryption and a private key for decryption. The public key is shared openly, and it's known as a public key because we do give it out openly, while the private key remains confidential. This approach solves the challenges in being able to sharing keys, because it's really hard in a symmetric encryption to make sure that we share a key with somebody else without it being compromised. Asymmetric encryption is used quite often in data exchanges, in digital signatures, and establishing secure connections, such as web traffic, SSL, and TLS protocols. So if we go further into symmetric algorithms, we can see how it looks. Because as I said, symmetric algorithms themselves uses the same key for encryption and decryption. Now, if we look at this diagram here, we can see we have some text. We encrypt it with a key. It's unreadable while it's encrypted, but in order to get it back, we use the same key to decrypt it. Okay. Some of the common symmetric algorithms out there are AES. It's the most widely used algorithm as of today. It was established by NIST and considered the gold standard as of today. AES could have different key lengths all the way up to 256 bits, and currently is still a strong encryption. Our next encryption is Data Encryption Standard, or otherwise known as DES. And it was one of the earliest symmetric encryption algorithms. It actually was developed in the 1970s. It only uses 56 bits, but it is vulnerable to brute force attacks, because of its short key length, and so we no longer use it. We have the triple DES, otherwise known as 3DES, and it uses the DES algorithms 3 times with different keys, making it more secure than DES alone. Now, DES itself is slower than the modern encryption like AES, so it's not highly used because it has a slow performance. But it can have bits of key sizes all the way up to 168 bits. Next, we have Blowfish. It's also a symmetric block cipher. It's an alternative to DES. It's known for its flexibility and speed. And while it's secure, it's actually used a lot of times in password hashing and file encryption. There's a lot of you can have a lot of different key sizes ranging all the way up to 448 bits. We have Twofish, which is an advanced version of Blowfish, and is one of the more. It was one of the finalists for AES, so it's known as the alternative for AES. It can have key sizes up to 256, but and it often is used because it still has strong encryption and high performance. And then we have RC4. RC4 is a stream cipher, one of the weird ones like that, rather than a block cipher, meaning it encrypts 1 bit at a time. While RC4 was widely used, it does have some vulnerabilities. So it has key bits all the way up to 2048, but we no longer use it because there's several types of attacks that have some weaknesses in it and some vulnerabilities, so we don't use RC4 anymore. Just know that these are symmetric type encryption. So talking about strengths and weaknesses of symmetric, well, it's definitely fast and efficient, it's very simple, and it is definitely secure for short-term use. Because the weaknesses is, how do we get that secured key around? We have to get that key, the shared key, to the other side. And then we have scalability issues. Because a unique key must be exchanged, it makes it very complex as the number of users increases. Now let's look at asymmetric encryption. So asymmetric encryption, again, is known as public key cryptography, and it uses a pair of keys for encryption and decryption. It uses one key to encrypt and a different key to decrypt. It's very useful here. So with asymmetric cryptography using 2 keys, the public key and private key are mathematically related, but they are unable to derive the private key from the public key. So if you had one key, you couldn't figure out the other key. Okay. So if I wanted to send you a message and I only wanted you to open this message, what I would do is use your public key because you're the only one with the private key to decrypt it. Now everybody has your public key, but you should be the only one with your private key. Now I could flip this around and I can encrypt something with my private key and send it out to everybody, and the only key that could decrypt my message would be my public key. So now you know it truly did come from me and nobody else. Asymmetric encryption is used quite often in our environments, and let's talk more about it. So let's look at a couple of the common key structures for asymmetric encryption. Probably the number one asymmetric encryption right now is RSA, made by these 3 gentlemen here. They have 496 keys as the strongest encryption there is. And it's used a lot of times in SSL, TLS, in other words, websites, or even PGP encryption, so aka email encryption. Okay, they're very secure, but they are slow at encrypting large amounts of data. So normally we use asymmetric encryption for certain things, and then if we wanted to do a large amount of data, we would go back to symmetric key encryption for other things. Another one is the ECC, which is the elliptical curve cryptography. Elliptical curve cryptography is an asymmetric encryption. It uses smaller key sizes. Normally it's 256 bits, which is equivalent to a 376-bit RSA key, which is really cool. It's used a lot of times in digital certificates and mobile devices, particularly in like SSH connections. In other words, secure shell connections. It's actually more efficient and faster than RSA, but its weaknesses is it's more complex to implement. So older systems really don't know how to handle ECC, so we still use RSA in most cases. Now we'll have Diffie-Hellman, which is DH for short. We used to use this one, but the problem is it's vulnerable for man-in-the-middle attacks because during the shared key exchange, it's very easy to capture those keys. So we just don't use it anymore. And then you have DSA. DSA could have key sizes quite large, up to 372 bits. And it's used sometimes for secure email. A lot of secure email like S-MIME uses this. But the problem is it's slower than RSA. So we normally just don't utilize it that often. Now talking about the asymmetric strengths and weaknesses. Asymmetric is strong because of key distribution. It makes it a lot easier. Authentication and non-repudiation is pretty easy because we have a public-private set. Now with that said, sometimes it's harder because it's slower than symmetric encryption. And then now we've got 2 keys for every individual that we now have to find a way to manage the key sets with. So let's talk about hashing. Hashing is a cryptographic technique that transforms the input data, such as a file or message, into a fixed string of characters that represents a sequence of hexadecimal numbers. This hash value, otherwise known as a digest, is a unique number specific to input data, meaning that even a small change to the original data will significantly change the hash value. The way that this works is I can put in text into a hash value, output a string, and if I change anything here, it will output a completely different hash value. This helps us to identify if there were changes to a file as we went along. It's used quite often in forensics investigations and also ways to identify file integrity. Many of you have probably used file integrity checks either in your operating system or in your game systems. And all it's doing is double checking that all the files meet the same hash as before. If they determine that it's a different hash, then the file has been altered and they'll fix that file. Now that alteration could have happened by corruption or even by a malicious attacker. Some common types of hashing is MD5, uses 128 bits hash. We normally don't use this anymore because there are things called collisions where we can get 2 inputs that output the same hash. So we don't use MD5 hardly anymore. We have SHA-1, which pretty much does the same thing but with a 160-bit hash. It's used for digital signatures and certificates. But again, we have collisions on this one as well, so we don't use it hardly at all. And then we have SHA-3. SHA-3 is the last member of the SHA family, has bits all the way up to 512, and it's built on a secure algorithm with a different underlying algorithm of SHA-2, and it's still highly used. It's probably the one that I recommend the most is using a SHA-3 algorithm when we're dealing with hashing techniques. Lastly, we have RIPEMD uses 160-bit. Because secured, it's very secure, but not highly adopted. Almost everybody still uses SHA-3. So what do we use hashing for? Instead of storing your password directly in a database, a lot of people will store a hash of your password. This way it protects it a little bit and ensures that if it does get compromised, the attacker doesn't have the password, but rather just the hash of the password. We could look at file integrity verifications. As I said, this is how we can determine that the file itself was not tampered with. We can use digital signatures, and digital signatures help ensure integrity of messages or documents. I might put a signature at the bottom of an email so you can double check that it truly is from me, or that that email was not changed in transit. And then lastly, we've got blockchain technology. We'll talk about blockchain a little bit more, but it's definitely an integral part to make sure that there are integrity between all the blocks within blockchain. Now we can improve this process by adding what we call salting. Salting is a technique where we increase the security of hash data by adding another string of text into our source string to make sure that it doesn't fall prone to a rainbow table or a dictionary attack where attackers have already pre-computed hash values of commonly used passwords. By adding a salt to it, it adds a layer of randomness to the input before it's hashed. This makes it a lot harder to decrypt. So how does salting work? We normally generate a random salt. We combine the salt and the input. We then hash the input, and then we store the salt and the hash separately from each other, so that way we can use that salt somewhere else. Now the key here is, how do we keep the salt and hash separate from each other and secure, in case somebody gets into the system, that somehow they don't get both of these pieces of the puzzle. So here's an example of salting. Let's say we have a password, very weak one, called password123. We generate a random salt. We add it to the password. We then hash the password, and the resulting hash and salt are then stored in the database. It's pretty cool. Let's talk about PKI. PKI infrastructure is a system that enables us to communicate, authenticate, and have data encryption by default. Most of the time using pairs of pairs of keys. Okay, we're talking about public and private keys. We're talking about asymmetric encryption. Okay. This is basically how we get a framework to ensure that, hey, are we doing this properly? Now, where is it used at? Well, again, we have a public and private key. So public normally is distributed to the wild. Anyone can access the public key. Private key is our secret. We don't share that with anybody to make sure that our public and private key are still secure. It's used a lot in digital certificates. So when you go to a web page and you see that it is a authorized web page, then this digital certificates themselves have been validated as good certificates. That way, if you're using like a banking website, you don't have a problem with anything. Now, someone's got to give us these certificates, so we have what we call certificate authorities, and these are the ones who are responsible for issuing, maintaining, and even revoking digital certificates to make sure that you are who you say you are. We have registration authorities, which will help us verify the identity of entities before a certificate is even issued. So the CA does the issuing and managing and revoking of digital certificates. The RA ensures, hey, let me make sure they are who they say they are before you issue the certificate. Then you've got their certificate revocation list, the RCL, the CRL. We had a little dyslexia there for a second, which is a list of certificates that have been revoked before their expiration list. So most certificates can expire by a certain day, but if for some reason, let's say our private key was compromised, we might want to revoke our certificate. And so the CRL allows us to know that, hey, although the certificate was technically valid, we revoked it early, so now it's not valid. And then we have our online certificate status protocol, the RCSP. And this is basically, well, how do we know if a certificate is still valid? Well, we use OCSP to ensure that, hey, is it on the CRL? Maybe. But OSCP is automated. So the OSCP, the OCSP, I can speak today, is there to help facilitate between the digital certificate, the public and private key pairs, the users, and just make sure that all data integrity is there. So what's this process kind of look like? Well, when we're dealing with a PKI, the first thing that we need to look for is the certificate issuance. So this means that an entity like a website owner will request a digital certificate from a CA. The CA will verify the entity's identity and issue the certificate, which includes the entity's public key and a digital signature from the CA. This way, if you want to verify if the certificate is valid, you can ask the CA, hey, does this public key match your private key? If it does, then it's a valid certificate. Then a secure connection is established. So let's say you open up the website. The server will present its digital certificate to the client. The client will verify the certificate by looking at the CA. And if it has been verified, not expired, or even revoked, it says, okay, we're good. The client then will ask the server certificate to decrypt a random session key. The session key will then be used in a symmetric encryption method during the session, and will only ensure that the server can decrypt the session key by using its private key. Because what we'll do is we'll send it the key through its public key, and only it can decrypt the key. Once that occurs, then a secure connection is established. This allows us to have client-server communication, then to make sure that confidentiality and data integrity is being met. Because at that point, we can then do authentication and integrity checks, because if we need to authenticate the other party, they can use digital signatures. A digital signature is created by hashing a message, then encrypting the hash with the sender's private key. The recipient can verify that the message through the sender's public key. So what does this kind of look like? Well, we can get into digital certificates, basically showing that, well, how do we prove ownership of a public key? What I can do as a sender is I'll take the digital signature creation. I'll use the sender's private key to secure it. It will be then sent to the recipient, and then we'll try to use their public key to decrypt it. If we can decrypt it with their public key, we know we're talking to the sender. Now, when we're talking about CAs a little bit, there's a lot more to CAs than just the handshake process. Once we have the CA, there's a lot of other things in that information. It's like, who was it issued to? When does it expire? There's a lot of pieces to a digital certificate. So there's like the public key, the owner's information, who issued the certificate, when is it valid, what is the serial number for the CA, and this is for the CA to be able to track that certificate. Is there a digital signature? And then what algorithm is the certificate made in? Is it SHA-256? Is it RSA? What is it using? Now, what types are we going to see in the wild? We're going to see types like SSL, TLS. These are common for web browsers. You're going to see code signing certificates. These are used for software developers. So when you download an application, can you see that that application was signed by the developer to verify that that code has not been changed, in storage or transit? We use email certificates for S-MIME. This helps us identify whether or not emails themselves were sent by the proper people and only that the intended recipient can read them. Especially when you're dealing with sensitive information, we need to make sure we're using these. We have client certificates. These just ensures that an individual device or user is verified before allowed in. Think of like a VPN client. You have to have a certificate for a VPN client to work. You might have a wildcard certificate. So you may only have one certificate for certain things. Let's say you have a website, website.com. But if I have a blog.website.com, do I need another certificate? Well, without a wildcard certificate, the answer would be yes. But I could get a wildcard certificate like star.website.com, and any subdomain on my website can use the same certificate. And then we've got our EV certificates. EV certificates are the most expensive certificates, but that's because these type of certificates go through a huge background check before they're issued. These require a more rigorous verification process. Okay. So we've already talked a little bit about this, but how does this look? You can see how the end user itself will talk to the RA. I want to request a registration. They'll confirm identity. They'll send the registration to the CA. The CA will then be okay with this. RA will then send a ID and password back to the end user, which then we will then install on the clients with our key pairs. Once we have it there, we will then request our certificate from the CA. Then the CA would issue us our certificate. We would publish the certificate to a vault. We would then download said certificate and utilize it. It is a long process. It looks long, but this is how it makes sure that we are secure. Makes it a lot harder to to get around. Now, if we're thinking about blockchain is a decentralized ledger technology. Really what the key here is once the data is recorded, it is extremely difficult to alter to ensure integrity and secure of the data. So blockchain is used all over the place, not only for cryptocurrency, but used for many different things. But there are some key concepts of blockchain that you need to be familiarized with. So blockchain itself is decentralized. It means it's not just in a single server or system, it's everywhere. Not one single entity has control over the entire network. That way, no one holds an entire blockchain, ensuring that the system remains operational and secure even if some of the nodes fail. Now, you can make sure that it's immutable, which means once the record is made on the blockchain, it cannot be easily altered or deleted. It uses hashing to make sure that a block cannot be altered. Okay. We have consensus mechanisms called proof of work and proof of stake, basically making sure that everybody validates and agrees on the state of the blockchain. So that way, if one node says something different than the rest of the nodes, they can figure out, no, that's not right, and fix the problem in the puzzle. Proof of work, also called miners, complete to solve the complex cryptographic puzzle. The first node to solve it gets to add it to the next block. And then that's what happens. So this is how cryptocurrency works. Now, proof of stake is validators that to make sure that the next block are based on the number of coins that they hold in the network. Think of this as just a validation point of like, these are the hashes. Yes, this is correct. They validate the work, and now it's 100% official. We then use cryptographic hashing to make sure that each block contains the previous block's hash along with the transaction data. This is a one-way function that generates a fixed output size of an input. So even if one character is changed, the hash will change completely. This makes blockchain secure. And then finally, we have what we call smart contracts. Smart contracts are agreements written into the code to ensure that they automatically execute and enforce with every condition that's met. Smart contracts are stored and executed in blockchain, ensuring that transparency and they're tamper-proof. So how does it kind of work in layman's terms? Well, we'll have a transaction initialization, we'll create the block, we'll have a validation and consensus period to make sure that that block creation is valid. The block will then be officially added, and then the record will be created. Remember, the record's going to have a hash of the previous block, and then the transactional information of the current block. This ensures that we have a consensus and validation of every block that is created. There are a lot of different block types. You can use public. Think of this as cryptocurrency. You can have private. These are not only about cryptocurrency. They could just be validating transactions across the blockchain. You can have a consortium, which is a group that is governed over this blockchain itself. Or you can have a hybrid version where there might be some that's public, some that's private, allowing certain data to be private while others data to be private. Think of this like financials. We don't want the transaction data always to be public. Sometimes we want it to be private, but maybe we want the blockchain itself to be public so we can validate and verify that it is valid and there aren't anything weird going on with it. You're going to find it all over the place. You'll find it in cryptocurrency. We already know that one. You'll find it in supply chain management, providing transparent and tamper-proof records. FedEx and UPS uses this already to make sure that their tracking of their packages cannot be modified after they've been scanned in or moved. You can use it in healthcare to securely store and share patient records. The Eclipse system in healthcare already uses this. We can have smart contracts to automate that contract terms without intermediaries. Think of this like DocuSign. You have digital identities, which could help you with just to make sure that a user is exactly who they say they are. And then we've also started implementing it into voting systems to ensure that voting records cannot be tampered with. These are different encryption tools. You should know at least what they are. And so as we move through them, I'll just go through them real fast. We've got OpenSSL, which is a tool to make sure that we can implement like web pages. Think about SSL as in HTTPS. We got PGP, which is an open source version of email security. We got Vericrypt, which is a way that we can encrypt files on a hard drive. We've got BitLocker, which is built into Microsoft Windows to also use AES encryption to protect the entire hard drive. We've got TrueCrypt, which is no longer currently maintained. There's a typo on the slide. It's TrueCrypt. It's no longer maintained, but is still popular as open source encryption is still around. A lot of times we're talking about storage devices again. We got FileVault, which is Mac. This is Apple's built-in encryption tool. We've got Wireshark. Wireshark is a great network analyzer to capture and analyze network traffic. While not an encryption tool itself, it helps us monitor for encrypted traffic. We have SSL Labs, which is a Qualsys tool. Uses SSL implementation on websites. This is all about HTTPS again to make sure that we don't have weak ciphers. We have TLS, which is a widely used encryption, mostly in HTTPS and email again. We've got IPsec, which is commonly used in VPNs. We've got SMIME, which is a internet email system for security, used for a lot of times in corporate email systems. And then we have IKE, which is also used in the IPsec protocol set a lot, which helps us share security keys between two parties, again used for VPNs. All right, let's move on to obfuscation. Obfuscation refers to the techniques used to deliberately make data, code, or communications more difficult to understand or analyze. While this is not encryption, it is definitely a technique that we use to conceal sensitive information, complicate reverse engineering, and just protect our overall intellectual property. You'll find different ways of doing this. You can do this through code obfuscation, which is the process of making source code more difficult to read or understand. You can find it in data obfuscation, which involves altering sensitive data, making it not easy to read or recognizable, even if someone gains unauthorized access. And then we've got communication obfuscation, where we use it and where we try to hide what kind of data type we're using. So it's often used in malware, where the goal is to hide communication between a malicious program and a control server. Different techniques that we use today is we use renaming, which is just renaming variables and functions and classes to meaningless or misleading names. Just for example, we might rename a user password to A1 to make it harder for an attacker to understand what A1 is really used for. We might flatten our code, which makes it a lot harder to follow because no longer is it symmetrical. It's not from top to bottom. We might use loops or jumps to make it harder to analyze or reverse engineer the code. We might change our code to have control flow obfuscation by structuring the program to alter its functionality. By putting a ton of meaningless instructions and altering the order of the code that it's executed, this makes it harder for the attacker to follow our programming. Now we may use data masking, which is just hiding sensitive information with fictitious data. This once the data is altered, but the structure remains the same, so the masked data can be used for testing and development purposes without revealing real information. We can use string encryption. String encryption just uses things like URLs or passwords or other things and encrypt them in the source code. These encrypted strings can only be deciphered during the program's execution, making it harder for the attacker to extract sensitive information through static analysis. We can use dead code insertion. Dead code insertion is, again, adding a ton of code into a program, but does not do anything to the program itself. It serves no purpose. This is the only thing to complicate analysis of the program, making it longer and more difficult to reverse engineer. And finally, we can use packing. Packing is a very common technique used to compress and encrypt the original code to make it harder for any antivirus software analysis or anyone to really understand what the malware does. Packed malware normally decrypts or decompresses itself during execution, revealing its true functionality only then. We can talk about different attacks now. One of the attacks will be a brute force attack, basically typing all combination of keys or passwords until the correct one is found. Okay, we have a couple different ones here. We've got our dictionary attack, where is a method of breaking a password or cryptographic keys by systematically trying to pre-compiled list of all likely possibilities. Dictionary attacks are often used against weak passwords. This is what we're trying to go for. We'll have a dictionary of all common words and phrases, and maybe there are hashes that go with it, and then we'll try to implement each and every one of them until we figure it out. We've got the birthday attack. Birthday attack is the mathematics behind the birthday paradox, and which states that if you have a group of 23 people, there's a high probability that 2 or more people in the same room share the same birthday. So this is the same thing that we do. We'll do a birthday attack where we'll take 2 inputs, produce the same hash value, known as a collision. So we'll try to do a birthday attack by saying, hey, there's more than one output, so let's do that. We'll do a replay attack. Replay attack is maybe they've captured your authentication token as you were trying to log into a website. Maybe they can reuse it to replay it on the website. If they replay it successfully, the website would let them in and use the same session that you were logged in with. We've got a man-in-the-middle attack, otherwise known as an on-path attack, occurs when an attacker secretly incepts and alters communications between parties without their knowledge. A lot of times this isn't just about altering, but the attacker can decrypt, modify, and even re-encrypt messages before forwarding them on to the intended recipient. They can use this information for many different ways of doing it. We've got the chosen plaintext attack, which is when an attack occurs during an attacker can choose plain text to be encrypted. So remember when I was saying they take the plain text, get the resulting ciphers to try to figure out, okay, does one of these ciphers match the cipher I already have? If so, this is your password. And then you've got the chosen cipher, where they choose ciphertext and obtain decrypted plain text, where they will do the same process again. Instead of going from plain text to cipher, they're going from cipher to plain text. We've got a side channel attack. Side channel attacks are using physical characteristics of information like electromagnetic transmissions, power consumption, rather than attacking the algorithm directly. Think of this as if they could tap into the wire directly. They can then listen into your communication like a man-in-the-middle attack, or even utilize or piggyback on your connection. We now have a downgrade attack. A downgrade attack happens when the attacker itself uses a weaker or less secure version of a protocol to encrypt an algorithm, allowing them to exploit known vulnerabilities. So let's say you have a certain version that you use on your website, but maybe your website allows them to downgrade the version of encryption that you're using, which then has known vulnerabilities, and now they can use those vulnerabilities to get into whatever they want. And then we've got a rainbow table. Rainbow table is a pre-computed hash values based off of common passwords, and this rainbow table is used to say, I've got this hash, is there a pre-computed value of a password? All right, so that's the end of cryptography. There's a lot on this one, so please make sure that you read your materials, make sure you read the book, not only watch this video, to actually completely make sure that you understand the basics of cryptography. We're not going to be mathematicians for the SecurityPlus. Just make sure that you look through this, read the papers, go through your flashcards, and if you do that, you should be ready for the SecurityPlus. All right, I'll see you for the next one.